All right, so this next topic is really just expands on what we've already done. There's not a whole lot of new information, but there is some new things that you need to understand just for interpretation purposes. But when it comes down to it, the work you're going to have to do in the next assignment mostly is stuff you already know how to do. So just focus on mainly interpretation, the matrix notation, just so you can interpret things when you're reading about them, either in the book or if you're doing your independent research online. Understand how these problems are written in matrix form, just like when we created the simplex tableau. We're really just using matrices of numbers, and we're not thinking in terms of the systems of inequalities. We're thinking of them as matrices being multiplied together to create those inequalities. So focus on those kind of things just for interpretation purposes. If you have questions, please ask. This first video is just going to be about those basic interpretations just for notational purposes. So we'll start with just the idea. Again, if you haven't really worked with matrices before, you don't have to master everything. It's just interpretation. So when we say a matrix is an m by n matrix, it means it just has m rows of numbers and n columns of numbers. So in this example, A is a 2 by 3 matrix. And then again, from a general notational point of view, you'll often see a matrix given to you in this general format as some array of numbers, A subscript ij. I is just the row number, j is the column number. So A11 is 2 because 2 is in the first row and first column. That's all that is. The transpose of a matrix is just the idea of kind of reflecting rows to become columns and columns to become rows. This has a geometric meaning, which you should have gotten out of a linear algebra course. If you didn't, you may want to just kind of read about that on your own. But for our purposes, that geometric meaning is kind of hidden behind the scenes in what we're doing with duality. And you don't really need to understand exactly what it means. But that's what a transpose is. We're just taking the rows, making them columns. To understand this notation and how it's used to simplify things, you just need to know what multiplication of matrices are. So if I have a x and y, which are actually we call column matrices, so they're, say, n by 1, putting the t here allows me to write it as a row, and then I tell you it's actually a column. Just for putting it into a document, it saves space. So when you multiply matrices, you have to multiply in a way that makes sense. So you basically have to multiply rows by columns to get a number. So anytime you multiply a row of one matrix and a column of another, you get a number. And that number is just the dot product of those two, what are called really vectors. Again, from a linear algebra course, dot product has an interpretation. It measures an angle between vectors. It's related to that angle. But for calculation purposes, all you're doing is you're lining up the numbers, the first coordinates, multiplying them together, second coordinates, multiplying them together, and all the way to the last coordinates, multiplying those together, and then adding those things up. Again, if you take an example in the plane, take two vectors with two coordinates and compute their dot product, and then measure their angle between the two vectors, you can actually connect those two with an equation. So in a previous example, what we're really doing is we're saying multiply the transpose of 1, 2, 3 as a column times the column 2, 0, negative 3. So again, this is just notational interpretation. So again, in general terms, if you want to multiply two matrices, A times B, the order does matter. Because if A is an m by n matrix, and you want to multiply it by B on the right, then B has to be an n by something matrix. In this case, I'll put K. So the number of columns of the first matrix has to match the number of rows of the second matrix. It's because what we do is we take each row of the first matrix and multiply it by the column of the second matrix to get the entry of the new matrix. So in below here, we've got a 2 by 2 matrix times a 2 by 3 matrix. So the result should be a 2 by 3. In general, if I multiply an m by n matrix times an n by k matrix, I will get an m by k matrix. I'm just illustrating here in boldface that the 2 and 3, the first row of the first matrix, and when I multiply it by the second column of the second matrix, I take 2 times 0 plus 3 times 4. So that's 12, and that goes in the entry that's in the first row, second column of our resulting matrix. Again, you don't have to actually multiply matrices in this class, but that's what it means. So when you take a matrix, like we will in our linear programming problems, especially if we have a lot of variables and a lot of constraints, this matrix A is representing all those numbers and all those inequalities. So if you have like 5 times x1 plus 3 times x2 plus 4 times x3, those numbers are numbers in a matrix, in a row of a matrix. And our x will be basically a column matrix of our variables, x1, x2, x3, and so on. So to write A times x, what we're really saying is the first entry is the first row of A times the column x. So that will give us the left side of one of our constraints. And then the next entry is the second row of our matrix of numbers times our column of variables. That gives us the left side of our second constraint, or an inequality, and so on. Again, a simple fact of relationship for transposition is if I take AX, which will be a column, and then I transpose it, it becomes a row, and then I can multiply it by another column and get a number. The order of operations here can be swapped with transposes in the following way. I can take the transpose of A, multiply it by Y, and then that is a column, and I can multiply that column on the right by the transpose of X, which is a row. So these two calculations lead to the same thing. It's just an algebraic manipulation to see that's true, and you can find a proof of that online if you want to see it. So this is the whole point of all this, is just so that we understand the notation of it in terms of writing our linear programming problems in a very simple format, and then we deal with the numbers when we need to. So our typical maximization problem is z is some number which is equal to the multiplication of a column of numbers, c, which we transpose to make a row of numbers, and we take the dot product with a column of our variables, x1, 2, and 3, and so on, to give us a function that looks like c1 times x1 plus c2 times x2, and so on. So that's just shorthand for what our typical objective function looks like. And then for our constraints, again, inequalities for matrices doesn't make sense unless you would define it to make sense, and that's what we're doing. We're choosing to define inequality to mean component by component the inequality holds. So when we say x is greater than or equal to 0, what we're really saying is all the variables, x1 is greater than or equal to 0, x2 is greater than or equal to 0, x3 is greater than or equal to 0, and so on. And this middle part describes our other constraints. Just saying that when we take this matrix A and multiply it by our column of variables x, we get in each row is just a single number, and that single number is the ith row of A times our variables. So this is typically what we see on the left side of our constraints on a maximization problem. And then we're saying that that's going to be less than or equal to the ith row of B, but B is really just a column. It's just going to be a bunch of numbers in a column. So this is just a convenient shorthand for rewriting our problems. So in the next video, what we're going to say is basically just to understand how this notation can be used to describe what are called the dual problem of a linear programming problem.